Hi everyone! The purpose of this video is to walk through common pitfalls that I saw on the HL Paper 2 Final Exam 2021. You also have access to the mark scheme, so I'm not going to be redoing all of the work, just pointing out big things that I hoped you would notice in each question. There's a lot to do, so let's get right into it. Question 1 was about ethane 1,2-diol. My first step, if I were you, I saw some people doing this, but not everyone, would be to just go ahead and draw that molecule for myself. Okay, so question A asked about limiting reagent. We notice we have three gases here, and so here to the right of your screen, I'm showing you where in class we saw each of these concepts. So you really needed to apply the concept that we saw on day 11 with gases, because we did have gases. And so you can use gases as volume ratios. Let's see an example of this for carbon monoxide, and I'll point out some common pitfalls I saw. So of course, we'll start with carbon monoxide. I now need to convert to ethane 1,2-diol. The idea is to find the theoretical yield for each of my reactants and figure out which theoretical yield is smaller. That gives me my limiting reagent. So I can use these ratios 2 to 1 as volume ratios for carbon monoxide and ethane 1,2-diol to find theoretical yields here. Some problems that I saw, some people were trying to put moles here. That's not correct. It's not, you have not converted to moles without using that 22.7 dm cubed if you're at SDP conversion factor. I also found some people not converting to product. You do need to find the theoretical yield for each reagent. So not the moles of each reagent added, but the theoretical yield, the amount of product you would make if carbon monoxide is limiting and if hydrogen is limiting. Whichever makes less product is your limiting reagent, not whichever you added less of, whichever makes less product. In this case, those were the same thing, but that's not always true. All right, excess amount, we practice finding excess, as you can see to the right of your screen. Stoichiometry homework 9, question number 8. So to find excess, you need to find the amount. You start with, in this case, that was 1,000 cubic centimeters of hydrogen gas. H2 will be in excess because carbon monoxide is limiting. The amount you react with, in order to do that, use dimensional analysis starting with carbon monoxide, figure out how much hydrogen you need to react with 500 cubic centimeters of carbon monoxide. You subtract those and you get excess. Okay, so again, you can find all of my work in the mark scheme, just pointing out big picture things. In 3, here we were finding the amount of moles, given that we just found an the amount of centimeters cubed produced, the theoretical yield. So to go from volume to moles, you can use that conversion factor that we learned. This is from Stoichiometry Homework 8, which we actually did in class, even though it's called a homework, so you can use that 22.7 dm cubed in every mole of gas. And you're starting with your theoretical yield, which you should have found in A. All right, next question was about boiling point. Remember, whenever we boil or melt, what you're doing is you're breaking IMF. Remind yourself, I'm just going to draw some skeletal formulas here of the molecules they're talking about. 1, 2, and then ethene. Ethene is 2 carbons. So, whenever we boil or melt, we're breaking IMF. So I'm drawing 2 molecules or multiple molecules. So if I start with ethane 1,2-diol, ethane 1,2-diol would do hydrogen bonding between two molecules. It would also do London dispersion. So this is what's going to get broken when I boil or melt. Some people are still confusing IMF, like hydrogen bonding, with covalent bonds. So when I boil or melt, I do not break a bond within the molecule. All I'm doing is separating one molecule from another by breaking IMF. Same thing here. In order to boil or melt ethene, you would interrupt intermolecular forces. So now we just need to figure out which molecule can make stronger intermolecular forces, very similar to what you did in Key Assessment 5. And of course, ethane 1,2-diol can form these hydrogen bonds that we've shown. So stronger IMF, higher boiling point. C told you that we had an alcohol and it was oxidized to a carboxylic acid. We didn't really look at diols, but we did learn that there's one set of oxidizing agents for all alcohols, and that's either potassium manganate or potassium dichromate. And so you could have given either of these ones that I'm showing here on the right, and could have given either the name or the formula. Some people told me just oxidizing agent. That is not specific enough, friends. You need to name the oxidizing agent. If they're asking for a reagent, you need to give a specific reagent. So in this case, potassium manganate, or you could call it potassium permanganate or potassium dichromate. Any of those work. All right, moving on. Question 2. Oops, sorry, I just flipped ahead. It's a little complicated to go back. So you have access to these slides here. So 2A, deduce the equation. Well, the equation, I was kind of surprised some people struggled with this. It just had you read the problem, really. So, oops, I got that wrong. 3NO3. Decomposition, we saw decomposition reactions. We watched a video with reaction types. So I have this compound that decomposes, meaning one compound forms several compounds to form nitrogen gas. I know nitrogen is diatomic, so nitrogen gas, plus water vapor, plus carbon, solid carbon particles. And then you just need to balance the reaction. You did need to balance there in order to get full points. I believe the coefficients were 2 and 3, and then that might get us to balance. Let's see, 4, 3 oxygens. I think that's right. Yep, we're good. Okay. Question 2B, 10 grams of moles, 10 grams, of reactant. Calculate the moles of gas produced. Some people only looked at the reactant and they didn't get as far as moles of gas produced. So in this case, we're going grams to moles using molar mass. Most of us got that. We learned molar mass pretty early on, day 2 in stoichiometry. And then moles of reactant to moles of product. Well, moles of one thing in a reaction to moles of another, that is coefficients. In this case, it was asking about all gases produced. So I'm looking at both gases produced, the nitrogen and the water. So 5 gases produced, or 5 moles of gas produced for every 1 mole of reactant. 2C, this was a PV equals nRT problem. People generally did well. The issue that I saw there, the only real issue I saw there was forgetting about the units. Just like it tells you on this slide, units matter. You need to convert to the correct units. So you needed to convert 127 to Kelvin and decimeters cubed to meters cubed. And then at the end, you needed to convert your pascals to kilopascals. D. People struggled a little bit with D. I was a little surprised by that. But I guess we'd only gone over it once in class. So in D, why does water deviate from ideal behavior when the gases are cooled? So if you look to the right of your screen under low temperature, notice that gases deviate from ideal laws at low temperature when they have some IMF. Okay, so I know that in general, when gases are cooled to a low temperature, they're going to deviate from ideal behavior because all of a sudden they start having some IMF. One of the principles of an ideal gas is that you have no IMF, and so if you start forming some IMF connections, well, then you're going to deviate from ideal. Notice that they're still gases. So some people were trying to tell me about a phase change. That's not what we're talking about. We're talking about gases and if they're acting like real gases or if they're acting like ideal gases. Okay, so now I need to compare water and nitrogen. Well, which of those is more likely to have some IMF? Water is, because water can do hydrogen bonding. Nitrogen cannot. All right, moving right along. Question 3. So question 3A was generally well answered. You did need full electron configuration, so some people were trying to give me abbreviated. Some people also did not remember that copper is an exception. So if you read through, this is from the question document, you'd also practice doing the electron configuration for copper. You did need to know copper. It is an exception to the normal rule. It fills 4s with just one electron, and then at the end there fills 3d. So kind of unusual because Aufbau tells us that 4s should fill before 3d, but copper is an exception. 3b, state one difference in physical properties and explain why the chemical properties are the same. Physical properties, some people did try to tell me mass. We actually saw that same question on topic 2 key assessment. It is atomic mass, but physical property of the whole substance. You could have used melting point, boiling point, density, an actual physical property, not just atomic mass. Explain why their chemical properties are the same. A lot of people said because they have the same electrons. The IB is really picky with this question. It's really because they have the same electron configuration, right? The same valence electrons, because valence electrons are what bond and give something chemical properties. Or they also accepted same number of protons and electrons, right? These are isotopes, so they only differ in neutrons. One other thing to notice here, this is the mass number. Oops, my pen just disconnected. That 63 and 65, that is mass number. I saw some people trying to talk to me about having 63 electrons. Careful, mass number. All right, explain why zinc is colorless while copper is not. Well, we'd seen that exact question. We saw that in the high level time. It's because zinc, when it forms complexes, it does not split the D level, but it has a full D subshell. Some people were just trying to say it's full. You do need to be specific. It has a full D subshell. It has unpaired electrons in 3D copper, and so the D subshell or the 3D, the 3D energy level can split when it forms a complex ion. People tended to confuse a little bit C and D. So D subshell splitting, that's why we get those colored complexes. Why do we get variable oxidation states? That's because 4s and 3D are similar in energy. So it's subtle, but in C, we're really looking at the fact that D splits, 3D splits into not just be n equals 3, right, all at the same energy level, but that the different orbitals in 3D actually are at two different energy levels. Why do we get variable oxidation states? Well, because we can pull off outer electrons from either 4s or 3D since they're so similar in energy. So in C, you shouldn't really be mentioning anything about the 4s electrons. That's not super relevant. The color comes from the d orbital splitting. And then in question 3D, you should talk about 4s and 3D similar energy. All right, this one was a little tricky. I know we didn't practice it a ton. We did see it in class. Okay. Calculate the ionization energy for a single atom of hydrogen. So notice that the units that they give you in the data booklet are, I believe, kilojoules per mole. And they were asking you for a single atom. Well, if I'm in kilojoules per mole and I need to get into a single atom, I should be able to, obviously, whatever number I have, I can pretty easily convert to joules. So multiply that number, 1 kilojoule, 1,000 joules. I also am going to need to get from, remember this unit was kilojoules per mole, I'm going to need to get rid of that mole and get it into individual atoms. So if I want moles to cancel, moles start out on the bottom, so I'm going to put moles up on top. And Avogadro's number is 6.02 times 10 to the 23 on the bottom. And now my kilojoules have canceled to leave me joules. My moles have canceled to leave me atoms or individual atoms. And now I'm in the unit joules per atom. Well, that's great. Joules for a single atom. So you had to look up the ionization energy for hydrogen in the data booklet, and then this was the process you needed to do. Um, if I'm being honest, I did mean for these both to be copper, and it ended up being one copper and one hydrogen, so a little confusing, but I was really, really careful in the grading, and if that seemed to trip anyone up, I was generous with awarding points. I don't think that actually really affected anyone, but anyway, determine the frequency. Well, you needed to use this formula. E equals hv. So sections 1 and 2 of the data booklet, you were looking up Planck's constant. You were finding the energy from copper, and then solving for frequency. So we had, in the HL atomic structure review homework, we did have a problem where we practiced using these formulas. You do need to be able to use both of these formulas, E equals hv and C equals V lambda. These are formulas you need to be able to manipulate. It was only 1 point, but worth going over because it could show up on the IB test. All right, problem F. Ammonia is added to copper 2 chloride, dark blue ion. It asks you for the geometry and the bond angles. Well, you can see here when we did geometry of complex ions, all I'm doing here is I'm just counting the ligands. I have 4 plus 2 is 6 ligands. I know that I don't have any lone pairs because I know that I needed an expanded octet in order to form the complex ion. So there's not going to be any lone pairs in that central ion. So if I have 6 ligands or ligands, however you want to say it, that means I have 6 electron domains. 6 electron domains is octahedral, and the bond angles are 90. So this is octahedral, 90. And these were shapes and angles that you needed to know from HL time. All right, moving right along, question 4. So here's where you had an example of this definition, the nature of ionic bonding. A lot of people got tripped up here. People were trying to talk to me about how an ionic bond forms Remember at the beginning of this unit, we spent a long time talking about the difference in the electrostatic attractions between ionic substances and covalent substances. So there were two key things to getting this point, just like you see on the question to the right on your screen. So you needed to mention having a positive and negative ion and the electrostatic attraction. The IB doesn't use the words cation and anion so much. You might have used them in grade 10, but mentioning that you have positive and negative electrostatic attraction. I saw some people using the word atom, which really, really concerns me. Remember, by definition, an atom is neutral. So ionic bonding, you have ions. So if you had anything about an atom, unfortunately, you did not earn that point because you do need to talk about ions. B. B was interesting to me. You had to, instead of doing the formula, you had to describe the formula. So we did many practice problems where we looked at a mass spec and we found the relative atomic mass. Some people kind of struggled with how to describe that. That's why we work on summarizing and that sort of skill. So instead of doing the math, you are asked to describe it. So the fact that you're adding all of the isotopes' mass numbers times their relative abundance, and you look up those in the mass spec. For C, why were they colored? I saw some creative answers here, but colored, this is not the same as a complex ion situation. The colors that we see from sodium and calcium, those are not transition metals. This is just from when an excited electron falls. And you had to be clear that the photon comes out when the electron is relaxing back down to the ground state. So some people were making it sound like the color is when energy is being absorbed. That's not correct. The color comes when the electron relaxes. All right, 4D. 4D was really well answered. You just had to show a big gap. Calcium is in group 2, so there should have been a big jump or discontinuity after IE2. So you had some sort of increase, then a big increase, then it continued increasing. Something like that. So that was generally well answered. I was really pleased about that. All right, sigma and pi bonds. People struggled a little bit with describing sigma and pi bonds, so I've copied here the mark scheme from HL Homework Topic 14, Part 1. So you can read that closely. You did need to mention the direct overlap and then sideways overlap. So some people are just saying overlap. You did need to be really specific, head to head and sideways. Just like you see in the mark scheme. That's what they got points for. And then you just had to count the sigma and pi bonds. That was generally pretty well answered. All right, moving right along. Question 5. Explain why atomic radius decreases. So some explanation around Zeph, mentioning that Z increases or the nuclear charge increases, the electron shells stay the same. Those were the 2 points there. Some people were getting a little tripped up, so just be clear. Talk about the protons and then talk about the energy levels. The reaction of lithium with water, notice on the slide here, you did just need to know these reactions. With any alkali metal plus water, you get a metal hydroxide and hydrogen gas. And that's just a reaction you have to know. People did okay finding the compound. Some people were trying to write out a reaction. You just needed to list a compound. So for example, when we're looking at covalent bonding in topic 4, this is almost more of a grade 10 subject, to be honest, but you look at where these both are in the periodic table. Beryllium, of course, is group 2. Nitrogen is group 5. And so you need to figure out how to match those up. So this nitrogen needs 3 electrons. Beryllium is going to give up 2. The reality is that they're going to end up sharing but we would get something like this. And you could draw out that Lewis structure to confirm that for yourself. Okay. And you practice that same skill here in topic 4 at the beginning. This was kind of a mix in D here, but the Lewis structures that we saw in this case were equivalent Lewis structures. Equivalent Lewis structures always mean delocalized electrons. So the key there was saying delocalized electrons. Some people were just telling me that there's Lewis structures. True, but the question asks you about bonding. How do the bonds work? The bonds work in that the electrons are delocalized. They're not concentrated in one single bond, they're moving freely throughout the structure. Formal charge, you needed to set up the equation correctly. And that's an equation we learned in high level time. All right, question 6. 6A was about naming. We've practiced naming. Here's an example of where we practiced naming. This was generally well answered, but I did see some people kind of adding unnecessary numbers. So it was just methylpropene. Notice, so I'm going to label my carbons. There's no configuration where you could move something and still have the same methylpropene. If I moved this methyl group to carbon 3, it would be part of the chain and I would have butene. If I moved it to carbon 1, same thing, it would start forming part of the main chain. So the only situation in which I can have methyl is here. That means I don't have to give it a number. Saying 2 is actually redundant. Same with propene. Propene could only be on carbon 1 because by definition, you're going to start numbering wherever you have the highest priority functional group. So saying prop 1ene, again, that's redundant. So I accepted it if you added numbers, but I'm going to be honest, I'm not sure the IB would. So that's something to really pay attention to. Almost everyone, I don't think anyone eliminated the numbers, and the numbers in this molecule were redundant. So make sure to be really careful with that moving forward. People generally did well with the polymer. If you didn't, make sure you're going back to the slide and working out. You do need to be able to go from a monomer to a polymer or from a polymer to a monomer. And I know we've gone over that in class and office hours. So if that's still something you're struggling with, you should probably come talk to me one-on-one. I think that would be the easiest way to handle that. You should be able to do that skill, and that was generally well done. A3, complete combustion. I had some people saying something like CXHY. You needed to use compound A, not variables. You needed to use a specific compound A that we had, which was methylpropene, put this into a molecular formula, and then, just like we practiced in class, complete combustion will always be plus oxygen yields carbon dioxide and water, and then balance. B1 I should say, these were isomers because they had the same molecular formula. And the chemical test, I was surprised this wasn't better answered because we saw this chemical test in class. We haven't seen very many chemical tests. One person I thought was very creative and said maybe you could boil them and they would have different boiling points. That's true, but that would be a physical test. So the only chemical test, really the only chemical test we saw in the organic chemistry unit was a bromine test. You did have to be specific that it's not any halogen, it's bromine. And then you had to be specific about what results you would expect. I still see some people using the word clear, and you'll notice that in the mark scheme we saw, the IB specifically says do not award points if you say clear. So make sure that when you're describing expected results, you are using that word colorless. All right, question 7. So question 7, was explain the free radical mechanism. So you can see here, we did this plenty of times in class. We went over it. I told you it was going to be on the assessment. You just got to know that mechanism. Question B1 or 7B1, this was another one where I told you in class that it was going to show up on the assessment somehow. You do need to know the steps for making a solution. So some people were trying to do math. I gave you the numbers. You needed to tell me about lab techniques. And we'd seen this actual question in a homework problem. And I told you that this would be on the test somewhere. So listing any of these steps, you needed to list at least 2 of them to get those 2 points. This was a nucleophilic substitution for B2 because, well, sodium hydroxide is actually the only nucleophile that we've really worked with. So if you're dealing with hydroxide, you probably have nucleophilic substitution of some kind. And then SN1, this is another mechanism you need to know. This is, oh, sorry, I got ahead of myself. In B3, they're asking about leaving groups, so we saw that here in the slides, all the way to the right. You can see that the bond is weaker, and so that's why, let's see, the bromine, and let me be specific, the CBr bond is weaker than the CCl bond, and that makes, bromine a better leaving group. Better leaving group because the bond is weaker, it's easier to break, so it happens faster. All right, last question. Question 8. State the type of reaction in question 8. Well, we actually saw that. Really specifically, we saw that in the little check for understanding that we did, the last check for understanding, and it's actually an addition reaction. I'm starting with an alkene. Some people were trying to say halogenation, but the mechanism is addition. And we did practice that in the check for understanding right before the final. So I think some people really picked up on that based on that check for understanding, which was great. B, I accepted anything to do with Markov-Kovanov, however you say our friend's name, the rule that we learned in high level. We'll go over in August. The IB actually wanted a slightly more specific answer, but anything to do with this rule and where the hydrogen atom bonds, great. And then 8D, now we get to the SN1. Sorry, got ahead of myself earlier. This is SN1 because I have a tertiary halogen. And so, again, if I'm reacting with hydroxide, I probably have nucleophilic substitution, meaning either SN2 or SN1. I need to figure out which one it is. I have a tertiary halogen, so the faster mechanism will be SN1. And this is one of those mechanisms you just need to know. All right, I hope this helps. Reach out. Feel free to reach out with any questions. I'm here to support you. You've got this. Have a good day.